Hey, how are we doing? So I wanted to cover a concept in this video. I'm going to give two examples, this one and a second problem. I wanted to give a shout out really quickly to the person who taught this to me. This is going to be about the Shoelace Theorem. And recently I was teaching a class for Mathtopia, which is a teaching company. I believe it's based in Wisconsin. And one of the instructors there sat in on one of my lessons and actually helped me to understand how the Shoelace Theorem works. That was Dr. Junaid Mansouri. And so thank you, Doctor, for explaining how this works. See, there's things that I have to learn as well, just like you guys are learning here in this video, or perhaps in other videos. I'm still learning all the time and picking up new methods and improving myself, which is exactly what you should be doing. So we're going to look at the Shoelace Theorem. I'll write it here on the side. It's called the Shoelace Theorem for an obvious reason, which you're about to learn. Let's see it in action. It's the easiest way to explain it. By the way, there's two kinds of understanding, in my opinion. This is just the way I think of things. You can have operational understanding, which is how I survived linear algebra, and you can have like deep theoretical understanding of what's happening, right? I only currently have an operational understanding of Shoelace Theorem. I'm not going to prove it to you. I just know how to apply it, okay? Later down the road when I have time, probably in the off season, which is the time period immediately following the exams, for about 3 or 4 months, in the off season I will try to get down a proof for this and maybe prove it to you in the future if I'm capable of such feats. But for now, shoelace, I don't know. Anyhow, but it's not the same spelling. But let's get to it. Let's get a look at how it works in action, so that you can see it. I just kind of came across this question as I was teaching one of my own students. You can get tutoring by sending an email to me. It's on the About page. And in the problem, I came across this one and thought, man, this is the perfect opportunity to use the Shoelace Theorem. So I got a chance to apply it relatively swiftly after it was explained to me how it works. A quadrilateral, four-sided figure, has vertices there, where a and b are integers with a greater than b greater than 0. The area of PQRS is 16. What is a plus b? The Shoelace Theorem is essentially a way to find the area of any n-gon, right? Any polygon. It doesn't have to be regular. It can be irregular. It doesn't matter. You give the ordered pairs of the points, and what you're going to do is you can pick at any point you can start, and then you can just go clockwise or counterclockwise. And I'm going to list those points in order like this. We'll do A, B, because P is first. The next point you would hit is Q. We'll write B, A. And by the way, you don't actually need the parentheses. That's just kind of, I don't know, habit, I guess. So if you don't want to write them, especially you're doing a test, time is of the essence, fine just to write the points like this. Negative A, negative B, and then negative B, negative A. And the thing is, you're going to take this one and attach it to the bottom of it down here. So it's all the points listed with the first point written twice. Somebody else in the comments, if you guys do know a proof for this and you want to link it or something, yeah, I know there's a written proof, but maybe you know of one where somebody explained it super duper well and you would like to share it, feel free. Okay, all you're going to do is you're going to go this way and multiply this first term on the left with the second term on the right there. And what we're going to have ultimately is 1/2 times a certain expression that we're about to generate. A times A is A squared. And then you'll do it with like this, going like a shoelace would look almost. We're not quite to that point yet, but you'll see it in a second. B times negative B is negative B squared. And then negative A times negative A is going to be plus A squared, and then negative B times this B here is going to be minus B squared. Then we are going to subtract, okay, and it's in absolute value, keep that in mind. We're going to subtract going the other way. So from this A up to this negative A is negative A squared, and this negative B up to this negative B is plus B squared. And this negative A up to this A is negative A squared. And this B up to this B is plus B squared. Now the thing is, what I'm guessing is the way it works is we don't actually know in advance which of these two expressions is larger than the other. we need their difference, but it could be in some cases, and probably the second video, that this one is going to be larger than this one. And so it gets reversed in the order, and that's what the absolute value is for, mainly because absolute value of x minus y is the same as y minus x. Those are equivalent. And so we're going to now simplify this. We've got an a squared here, an a squared here, a negative a squared, which is plus. Another one of those here, we essentially have 4a squared. Then we have negative b squared, that's negative 2b squared minus a positive b squared, minus another positive b squared, we have minus 4b squared. And we have 1/2, and this is the area of the polygon, okay? It doesn't matter if it's regular, this will work. When would you use this? You would use it when you have coordinates in a plane that make any kind of polygon and you need its area for some purpose. This is so important, I would add it to the small notebook. If you don't know what the small notebook is, it's in the playlist on my channel for the AMC 10 preparation playlist. It's the most popular playlist, and videos on my channel are on that playlist. And what is a small notebook? It's an idea explained in there, but it's distinguished from a large notebook primarily by size. This is the large one, and as you can see, this one's smaller. You're going to get a small notebook and write these kind of formulas and concepts in it. This is what you should be studying the day before the test, and probably reviewed at least once a week, so that you can reinforce these concepts repeatedly throughout the year. Okay, as it gets closer to test time, more frequent review of the concepts that you've written down works. Okay, so add it to the small notebook. You can learn about more of that in the How to Study video on that playlist that you can find on my channel. I will link it in the description. Okay, let's continue. This is the area, but it told us the area was 16. You're going to set this equal to 16. You have a couple options. You can go ahead and, I don't know, pull the 4 to the outside. So why? Because if I have the absolute value of 4, right, times the absolute value of a squared minus b squared, I don't need, right, this 4 in absolute value. It's just take it out. You can do that with constants, as long as it's, positive. And if it was negative, you would just switch its sign when you pull it out. So we're going to factor the 4 out, cancel the half here. That's going to give us 2. So we're going to have 2 times an absolute value equals 16. You'll divide by 2, get the absolute value of a squared minus b squared is equal to 8. Next up, the absolute value. What do we do with that? Well, you can do normal absolute value rules, or you could think back to a key fact they told us, such as a and b are both positive and a is bigger than b, therefore a squared is bigger than b squared. We don't even need the absolute value anymore. It becomes a squared minus b squared equals 8. And all of you right about now are probably saying, hey, that's the difference of squares. And you're exactly right. A plus b, a minus b equals 8. Now what? What else did it say? They are integers, which means we can think of this like a Diophantine equation maybe. And then we can, I don't know if it is that. I'm not sure if I'm using that correctly, but I think it is. Either way, we need integers that multiply to 8, and as a is bigger than b, neither of them are negative. Our options are going to be 8 times 1 or 4 times 2. That's it, okay? The a plus b will be bigger because they're both positive. Let's try a plus b equals 8 and see what happens. If we do this, you will get 2a equals 9 and have a sad face, because that's not going to result in an integer for a. But you then can just use the other one, and it will work out fine. Rather than do so, you're just going to change this to a 4 and this to a 2, right? So you're going to get 2a equals 6. Why rewrite the equations? Get a equals 3, since 3 plus something is 4. That something, b, must be 1. But we don't even really need that. You can just verify that it works, and you got integers for both. A plus b is 4. That is answer choice A. This was a problem 10, made completely trivial and doesn't even need to be graphed by the Shoelace Theorem. So thanks again, Doctor, for teaching me that. You can find Mathtopia in the description as well. They're a great company. We'll be right back with the second example of this concept at work. Alright, and this is the second video that I wanted to do to demonstrate as an example of applications or potential applications of the Shoelace Theorem. And so I heard a lot of kids talking about this on the AOPS forums. I'm sorry, I just don't remember ever learning it at some point in my past. So when I learned it and I saw chances to apply it, kind of your eyes just open up as you see the opportunities for this to be used. And it's really not that hard to get down. Sometimes, as in this problem, there's going to be a lot of algebra involved and you're going to have to know your log rules because we are dealing with logs. Let's get to it. The vertices of a quadrilateral lie on the graph. Oh, this is the 2020 AMC 12A problem 17. So it's recent, right? So this is a recent application of it, which means it could appear on this year's test. They used it last year. Why not? So lie on the graph of y equals natural log of x, and the x coordinates of these vertices are consecutive positive integers. So the x coordinates are consecutive positive integers. The area of the quadrilateral is horrible. The natural log of 91 over 90. What is the x coordinate of the leftmost vertex? So if you just think quickly about a log graph, it goes through 1, 0. All log graphs, all basic log graphs do, and it looks like this. It's got an asymptote here. You're basically saying that if it's going to be consecutive integers, let's just call the first one, say right here, we'll call it n, right? N is usually used for consecutive integers or x or something, but x is already a coordinate. So if we call that n, then the coordinate of it would be n comma natural log of n. Why would it be that? Because it's the natural log of x and we made x n. Logical, right? So then this is going to be n plus 1, which is consecutive integers. You add 1 to get to the next one, which means this will be the natural log of n plus 1. Oh, by the way, if you're not sure what we're about to do, please watch the previous part of this video. Maybe you clicked a direct link from AOPS and you got to this video from the solutions on there. I'm not going to explain again how this works. It's explained in the previous part of this video. Just move the thing down there, the little timer thing over, and you can watch the first video. Okay, so n plus 1, natural log of n plus 1. The next one would be n plus 2, natural log of n plus 2. And then n plus 3, natural log of n plus 3. Notice there's 4 consecutive points. It is a quadrilateral. We know they're going like this, like n plus 1, n plus 2. Now we don't know that n is 2 or anything. That doesn't matter. The whole point is it's going to be something like this. You're connecting, and you can't really tell what the lines look like because it's so, it's just not zoomed in enough for you to be able to see that kind of thing. But we have to add the top point to the bottom as well. We talked about this in the first demonstration of this concept. Now, the area of it is going to be, I'm going to start over here, 1/2 the absolute value of, and I'm just going to go this way. It's n times this one, which is going to be n times the natural log of n plus 1. And then it's plus n plus 1 times this. So I'm going to have n plus 1 times the natural log of n plus 2. And then plus, we've already done this one, now we're doing this one, it will be n plus 2 parentheses, make sure you put the parentheses, you don't screw this up, times the natural log of n plus 3. And then you're going to have n plus 3 times the natural log of n. Okay, now that is just the first part, right? Technically, you don't have to put parentheses around this because, yeah, it is what it is. But we'll put parentheses just because. And then it's minus the other expression. The other expression is the opposite direction of the shoelaces. So it's going to be minus n times the natural log of n plus 3, and then plus this one here, which is going to be n plus 3 times the natural log of n plus 2. Sorry for the tedious writing. You're going to go this way. You're going to get n plus 2 times the natural log of n plus 1, and n plus 1 times the natural log of n. Okay. Now, all of this is going to have a parenthesis around it and the absolute value on the other side. It's going to equal this expression, but we're out of space. We'll just do it later. Okay, as you can see, the reason it's called Shoelace Theorem is the middle part looks like your shoelaces. If you tied them, which a lot of people just slip their shoes on, that's what I do. But yeah, if you tied them, it would look like this most of the time for most shoes, right? And not slip-ons, yeah? Okay, so Shoelace Theorem. Then, we want to clean this up, and we want to kind of be quick about it, because we are doing a test, it's time test. It is problem 17, and this is going to make your job a lot easier, so if you can get it right, you're probably well past qualifying at this point if you're answering this question on the AMC 12. But that's okay. Let's see what we can get here. So the n times natural log of n plus 1. Do I have one of those over here? I have a natural log of n plus 1 here with an n that's going to distribute to it. In other words, but this has got a minus out front. That n distributed is going to cancel this whole term. Okay? Then I have an n times a natural log of n plus 2. I see a natural log of n plus 2 here, and the n that's going to distribute to it here, that n will cancel. The 3, though, didn't go anywhere. Okay? I've got a 1 times a natural log of n plus 2. I don't see how that's going to cancel anything. So we're going to keep that one. We will have 1/2, and we will have the natural log of n plus 2. That's this one right here distributing to this. The n got canceled. Now we're going to do the n, just the n only, times the natural log of n plus 3, and I've got one of those here. It's got the minus out front. This n, when it distributes, will cancel this whole term. But the 2 times natural log of 3 is left. So 2 natural log of n plus 3 remains. Okay, then we have n, this n right here, distributed, right? The natural log of n distributes to the n to give n natural log of n. And because of the minus sign here, this one and this one will now cancel. The n, when it distributes, when the natural log distributes to this, I will get an n natural log of n term that's negative that will cancel the positive version of this. If you're a little lost, it's okay. Pause the video, write everything down that was there, and slowly simplify so you can see what it looks like, okay? But if you're able to follow and you understand what I'm doing, then that's great. Okay, but then we also have the 3 times the natural log of n is left. So plus 3 natural log of n. Now, I'm going to have what? I've got the 2, I've got the 1. There was nothing else left. I didn't lose anything in here. I still have a minus sign. I'm going to put the parenthesis. This one was completely gone, but this one had a 3 left right here. And it's going to be 3 natural log of n plus 2. And then I'm going to have a what? This is done now. I'm going to have a 2 left right here, and it's 2 natural log of n plus 1. Then I'm going to have a 1 natural log of n here. 1 times the natural log of n. That's all in parentheses and all like this. Let's combine like terms. We're going to have 1/2. I've got a natural log of n plus 2 minus 3 natural log of n plus 2. That's going to be negative 2 natural log of n plus 2. I've got a 2 natural log of n plus 3, and there's nothing to combine it with. So it's stuck as is. All right, then we've got a 3 natural log of n, and I've got a 1 natural log of n, but it's being subtracted. So 3 minus the 1 is going to be 2 natural log of n. And then finally, what did we not cancel? We got the natural log of n plus 2, that's done. We did this one over here, that's done. We haven't done this one. It's minus 2 natural log of n plus 1. Okay, absolute value. This is still equal to the natural log of 91 over 90. Now we've got that put in from above because it says the area is. The Shoelace Theorem, if you don't know, used to find area for quadrilaterals when you know the coordinates, or polynomials, no, polygons, there we go, in the coordinate plane. Okay, let's keep going here. We got the half. Again, I'm going to pull this 2, this 2, this 2, and this 2 out and get eaten by this 1/2. I'm going to reorganize the absolute value to be the positive terms first. So natural log of n plus 3, that's this one, plus the natural log of n. Now, if these 2's are gone because of the half, right, then what is the log of a plus log of b, right? It doesn't matter what the base is. We'll call it c. If the base is identical and you have they're being added, this is actually log base C of the product AB. Okay, look up your log rules briefly, the log identities, whatever you call them, log formulas, I don't know what they're called. But yeah, the rules that you can use with logs, okay? So this is actually going to be multiplied with n. I have the natural log of n times n plus 3 because there's a positive sign in between them. Furthermore, the minus log ones get moved to the denominator. So it's going to become n plus 2 of the same log. This is all within a logarithm, okay? N plus 2 has got the negative, that's going to go down here. The n plus 1 goes down here. I'm sorry I don't have time to unpack logarithm rules in the video. I've got to teach again in like 5 minutes and I'm running out of time. So we're going to continue on here. It's all in absolute value, and it's going to equal the natural log of 91 over 90. Okay, so now what do we do with this absolute value? Well, here's a question. If you remember, right, natural log of 1 equals 0. If this number is less than 1, like over here, the y value is below the x-axis. Therefore, if this is currently less than 1, the whole log will come out negative. So how could we flip that? Well, let's see. We didn't actually know which of these goes first. We could have subtracted from the other direction, which would simply mean these were the positives and these were the negatives. But let's think. N and n plus 3, the product of them, is it more or less than n plus 2 times n plus 1? Why don't you pick any 4 numbers in a row and find out? 2, 3, 4, and 5. Is 2 times 5 more or less than 12? It's less, right? So these numbers, why 2 and 5? Because this would be n and n plus 3. The product of the numbers farther away from a centered value will be less than the product of numbers closer. I don't know how to explain that right now more than just that. So that means that this, because of the absolute value of the difference, we could have actually flipped the signs, right? So that it became, instead of this expression minus that one, it's actually that one minus this one. So in actuality, what you're going to get, with no absolute value needed, is the natural log of n plus 2 times n plus 1 over n times n plus 3. This will equal the natural log of 91 over 90. I don't need the absolute value anymore because we switched the order of subtraction, and now this has a larger number over a smaller, meaning it's past the 1 on the x value, which means the value of it is positive, and therefore no absolute value needed. The last thing we need to do, these are both got a natural log. We can forget about that. What else do we know? We knew they were integers, consecutive integers that were positive. Therefore, the product of these is going to have 91 be able to be obtained, which means one of them must be 13. The only possible values, because 13 times 7, is n equals 11 or n equals 12. If you try n equals 11, you will get what? You will get 13 times 12 over 11 times 14. That doesn't actually make 91. That's not going to work. Let's try the n equals 12. I get 14 times 13 over, the 12 plugged in here is 12 times 15. Now, 14 and 12 both have a 2. Cancel it out. 7 and 6, 91 over 90. It's a match. N is 12. We are done. Make sure we didn't do anything wrong. What is the x-coordinate of the leftmost vertex? We called that vertex N. Notice it's not really right by 1. That was just for demonstration. And the answer is 12. I really hope this helps you guys. We're getting really close to the test now. This should be one more tool in your tool belt that, should it come up, you're ready to apply it. Good luck on the test this year, guys. I'll try to have 1 or 2 more videos out before the test, and I should have solutions for all of the ones I can do the next day. Like immediately starting the next morning is the goal. We'll see what goes on. You guys have a good one. I will see you in the next video.